So if I have an infinite line of charge here, and I want to find the electric field at some point P, where this is a distance r away. I can do this, I can find the electric field, I can go through the calculus of it, or I can exploit Gauss's law of electricity. Gauss's law of electricity says that the electric flux is going to be equal to the enclosed charge over epsilon sub 0. So in order to do this, I need to create an enclosure, and I create a Gaussian surface here. Gaussian surface doesn't have to be a real one, it can be virtual. So I create a Gaussian surface here, where this is length L. Infinite line of charge here with a linear density of lambda, which would be delta Q over delta X. We'll just call that the X direction. Or dq over dx, depending upon if you're calculus based or not. And so my enclosed charge here is going to be, well, the length here, L. I know that the charge is going to be equal to lambda delta x, which is lambda times L. So that's the enclosed charge here. So the electric flux should be equal to lambda L over epsilon sub naught. So the electric flux, as we know, is the electric field times the area, or the calculus version, E dot dA. Now, the electric field at this point right here, well, if this is a cylinder of radius r here, there's no reason to think the electric field at any point along the edge here, all the way around in 3 dimensions, the electric field should be any different. The magnitude should be the same no matter where you are. Because it's infinitely long, there's no priority, there's nothing to say that this point is any different than that point because this line goes on forever in both directions. So my electric field, the magnitude of my electric field along the edge here is constant. My area vector, I'll just take this point right here, my area vector is that way. So at this point right here, it's that way. On the ends, it's that way, because remember, the area vector is perpendicular to the surface. Since my magnitude of my electric field is the same everywhere along this area, when I multiply times the area, I end up with, well, let's break it down. This is the electric flux on the left-hand side, we'll call this L, plus the electric flux on the right-hand side, plus the electric flux on the sides. On the left-hand side, my area vector is going to be this way, but my electric field should be that way. By symmetry argument, I know that for any point here, I have another point here, that this will produce an electric field this way, an electric field that way. Any of these sideways components will cancel out, and the only thing that's left has to be away from the line, argument by symmetry. And you can work through the 15 minutes of math in order to show that indeed those cancel out. So here, my electric field has to be going that way, my area vector has to be going this way, and so my electric flux on the left-hand side has to be 0. On the right-hand side has to be 0, but around the center here, it's not 0. And so this is going to be the electric field, the magnitude of the electric field, times my area of the sides here. And the area of the side is going to be 2 pi r L, basically circumference of the circle times the length. So I have lambda L over epsilon sub naught is equal to E 2 pi r L. So my electric field, L's cancel out, that's convenient since we sort of made up that length right there, is going to be lambda over 2 pi epsilon sub naught r. That's the strength of my electric field. The direction is going to be away if the line is positive or towards if it's negative. But that's the electric field. And properly, I should actually write that as E, just so it's not confused with energy.